I'm Josh Gomez.
And I'm Jessie Frazelle.
We're from KittyCAD, and we're in Chatsworth, California.
We're at Machina Labs, and they use robots to form sheet metal. They even use them to make this sign.
Let's go inside. So first, I'd like for the viewers at home, I'd like you to explain kind of the whole journey to get here. First, start off with your name, introduce yourself, and then the entire journey that got you to Machina Labs. At what point did you feel comfortable to start all of this?
Right. So yeah, my name is Edward Mehr, CEO, co-founder at Machina Labs. I come from a software background. So academically, I actually went to USC here in LA as a computer engineer. It took me a while to graduate. I left the school many times to work for different companies, did a large stint at Microsoft for a while, went to work at Google for a little bit. But eventually, kind of left the academic world to join SpaceX. And the reason I was really excited about SpaceX is that, when I was younger, I was always like fascinated about how do we, kind of have manufacturing and computer kind of, in a sense, combined. Because when I went to a school that was kind of like a boarding school. So I spent a lot of time kind of doing carpentry, learned welding, and they got fascinated by computers. So when I went to school, I started, focusing more on the computers, but always was thinking about how can you just, kind of bring this things that we're learning in the, in the CS world to the real world, to the mechanical world. So I was excited to join SpaceX. I was a software engineer there, and that's where I kind of started to see a lot of challenges we had with manufacturing. Every time you have to build a part, you pretty much have to build a factory for it. If you go to SpaceX when they were building Falcon 9, it was very hard to change the diameter of Falcon 9 because all the toolings, all the molds that are specifically built for Falcon 9 were strictly for that diameter. So you want to make a bigger diameter, that meant you have to build a new mold, new set of tools, almost a new factories, make lots of investment to enable a new design, which is a huge impedance for innovation, right? So when I was at SpaceX, I saw some of those challenges, and that's why I got really excited about relativity space. So I joined after that to the relativity space team very early on, and started working on 3D printing. And at the time, 3D printing was very exciting, and it still is, very exciting solution because we kind of go away from those hardware-defined factories to something that can easily be changed to do a different parts, different material. So I spent some time there, but I realized 3D printing, as great as it is, the type of parts that it can do is still limited. There's a lot of other parts in the industry that can be manufactured. It cannot be manufactured with 3D printing. So we started Machina to focus on other manufacturing technologies that can be as agile as 3D printing, but they can do the type of parts that 3D printing cannot do, like sheet metal parts. So that was kind of the journey from kind of computer science world to here.
That's really interesting. We have also another question that's kind of random, but Jordan Noon is one of our co-founders. We'd love to hear any secret stories you have about it working with him.
No, Jordan's great. Jordan was my boss. So I can't say too many bad things. No, I'm kidding. It was great. I think there's one story that I remember is that, we had our first build of the tank. So this is in the first building that Relativity Space had where we had the cell. And we were building I think it was like maybe a 10 to 12 foot tall tank. And that was like a week build. So I remember we had the couch in front of in front of the cell. I remember me and Jordan would take different shifts, like afternoon and night, sleep on that couch, watching the cell, make sure that throughout the whole week it doesn't get interrupted. These are early days, so the system was not as stable, because every time it would stop, then you had because the whole thing is heated up as you're welding, the thing is like heated up and expands a little bit. So every time the system stops due to whatever anomaly, you have like 2-3 minutes to fix the anomaly and restart the build before it shrinks to the point where you cannot restart it again. So it's like a lot of interesting, cool early startup days memories that we had with Jordan, and kind of like, being inspired by how entrepreneurial he is in terms of just getting shit done. So I only have mostly good stories. So
nice.
That's
Off
cool.
camera, we'll ask you more intense questions. Just kidding.
And for everybody that may not be maybe manufacturing inclined, can you explain the process? What is going on behind us? How is it forming sheet metal?
Yeah, so it's interesting. So traditionally, I'm going to start with the traditional way of sheet forming, which is basically through a process called stamping. What you do is you have to get a male and female die. You put a sheet, and then you put these in a giant stamping presses. You put a sheet in between the male and the female. You're stamping, and with like basic shear force and brute force, you form it into a shape, right? And the challenge with that is you have to make those dies. And those dies are very expensive. It can cost, I was talking with some of the folks at Tesla, for a side panel of a car, a die can cost up to $1.5 million.
Whoa.
Right? And you have to do multiple iterations on that die because the actual geometry that you need to get to is usually different than the part, because sheet is also tricky where you form it and you get it off the die, it jumps and it springs into different shape. So you're actually forming a different die, making a different die that's different than the geometry. So multiple iteration, it's very expensive and time consuming. And sometimes it can take up to 50 weeks before you get your first batch of parts, because you have to make through these die iterations, get your die, set up the stamping process and stamp it. So what we do is basically very similar to how we were forming sheets before stamping process, which is how a craftsman used to work. And it's like basically slowly hammering a sheet into shape, right? Before the stamping process and having these giant stamping presses, a craftsman or a sheet shaper, they will get a sheet of metal, start hammering it slowly into a shape.
Oh my God.
So it's not so, what we're trying to do is almost that, but with robots, right? Can the robot slowly deform the shape of the sheet without needing a die? So there are two robots on two sides. There's a sheet fixtured in between them, as you can see in this frame. The robots slowly basically pinch and deform the sheet into the final shape.
Okay.
Right? And like I said, it's very similar to how a sheet shaper works.
That's a really good follow-up into the next question, which is, you mentioned like Tesla, that's how they form like side panels. And for anyone that's watching who's wondered how a car kind of gets shaped or the side panels get shaped, this is a really good application. What are some other applications in which someone would need something like this?
Yeah, so sheet metal forming is the largest metal processing sector out of all. I think if you think about day-to-day, most of the metal parts you see on day-to-day are formed sheet metal parts.
Yeah.
You're talking about cars, you're driving in a freeway, you're not in a sea of sheet metal parts. Like everything around you is formed sheet metal parts.
Sure.
But even if you're like sitting in a building, you look at the ducts for the AC, they're all formed sheet metal parts. You'll sit in an airplane, you're pretty much in a sheet metal can. Heavy machinery, tractors, all the exterior is sheet metal. Electronic equipment, the casing for it, most of the times is sheet metal. So it's a $250 billion industry. And I think the next biggest is machining, which is around 110 billion, right? So like by order of a magnitude, almost 2 times larger than the second biggest.
Sure.
So the applications are wide, like I said, from aerospace, from defense, airplanes, rockets, heavy equipment, tractors, combines, electronic cases, everywhere you kind of find sheet metal parts.
That's cool. Yeah, at my previous company, we were building like rack scale servers, and the outside of our rack, also even the body of the servers themselves, all sheet metal.
Right.
And then we had this like very intense design on the side of the racks to make the like more aesthetically pleasing, kind of like Apple. But it was very hard to get that to be cheap.
Right.
Whereas I feel like if we had given it to you, it seems like it would have been a lot more efficient.
Yeah, no, you're absolutely right. I think it's the funny thing is, so traditionally, if you're not producing like, hundreds or thousands, mostly like thousands of parts, you probably don't think about sheet metal.
Right.
Unless you have to. Like, for example, you're making a fighter jet, you're Northrop Grumman, you're making this fighter jet or this plane, you want to make 20 of them, and there's no other way to make it, so you spend the money. But in most applications, it doesn't make sense unless you have thousands of parts that you want to manufacture. So one thing that's happening with us is that not only there's a good replacement for current sheet metal parts, but new applications are opening up. For example, right now around 10 to 20% of our business is composite molds. Traditionally, nobody thought about sheet metal as a composite mold.
Okay.
Because in order to form a sheet metal, you have to make a mold, so it doesn't make sense to use them as a mold.
Sure.
Right? But with us, because we don't need a mold, you can form a sheet metal part and lay up composite on top of it. It's faster, it's less waste, you don't have to machine it. Traditionally, composite molds are machined. So you start from a giant billet, you machine, and think about if you're making a wing of an aircraft, how much material you have to machine. So with us, we can form the shape of it, lay up composite on top of it, put it in an oven and cure it. So there are all these new applications that are also opening up that people who never thought about sheet metal are now coming to us and be like, can you actually do this part out of sheet metal? That makes probably make more sense with your process.
Interesting.
That's really cool.
Do you only deal with some of these large scale projects, or do you also do some of the smaller work?
We have done like parts as small as, like 5 inch by 5 inch. Sometimes even like 1 inch. I think we did like impeller blades that were like 1 inch by 2 inches. But most of our customers, at least in our early days, are coming to us with larger, more complex parts. Because the more expensive the mold is, the more likely we make more sense.
Sure.
So a lot of our applications is like, tank for a rocket,
yep.
or shroud for an engine, skin in an aircraft, where these large parts where you have to spend like, the mold would cost you $1 million, $2 million. Be like, okay, this is much more cost-effective way and faster way to do it. But in theory, we can do from inches to feet.
Okay.
What's the kind of craziest part that you've done?
I think the one that like got a lot of, depends I guess how you define crazy, but I think the one that like got a lot of people excited is that you could scan your face and form a mold of your face.
Oh, we saw that. Whose face is that?
Yeah.
You have like multiple. I think the first one was one of our engineers, Mark,
Okay.
who did his own face. We had Ashley Vance from Bloomberg here. We did his face. I know his wife was complaining about it because we gave him 3 of them and he was having it in the house, and his wife was complaining, "You're going nuts. Just stop accumulating
Stop
your
making my
faces
faces, yeah."
everywhere."
Sorry.
So I think that was like probably the funniest, more kind of like people got excited about it. I think the thing that I am personally actually was really excited about is there's this toroidal tank that NASA used to build. And toroidal tank is and you probably know this, it's a very good, efficient design for a fuel tank of a satellite, because basically it's like almost a donut that goes around the satellite. And you can get a lot of volume with a toroidal tank while you have everything else in the center of it, but it's very hard to manufacture. So what people end up doing is they're creating these spheric tanks and put a bunch of them around the satellite, right? And NASA used to do these toroidal tanks back in the 60s, and they have these bump formers that would bump them into shape and weld them. But then we lost that skill set. So not a lot of bump formers exist today. They either retired or they passed away, and nobody picked up that skill.
Whoa.
So they're like, okay, now we can't form those, toroidal tanks anymore. And if you want to form it, we have to stamp it. It's going to be very expensive.
Wow.
So they're like, can you guys actually bring that back? Can you form these parts with your technology? So it's like a very cool, for me, it was an exciting thing that like, oh, you were able to do back in the 60s. We haven't been doing it. It's a very desired design. But because it's so hard to manufacture, we're not doing it, and we can probably bring it back.
Yeah, you potentially brought back history.
Yes.
That's incredible.
Yeah, so it was
That's
very
cool.
exciting. Yeah, it's actually outside. You can kind of look at
Well,
it.
yeah,
Was that
we
the
saw
donut?
one out
Oh,
there.
yes.
Okay.
Yeah.
That thing
Okay.
is cool. I was like, how? And then I got closer, and it's like welded at certain areas,
Yes.
but then it's very curvy. And I was like, these robots can get super curved.
Sure.
Yes.
Do you guys do welding in-house?
Not at the moment. So we're focused on just really honing down forming and trimming today, which is pretty much 100% of our parts that are formed require some form of a trimming. But our goal is that in long term, we keep adding more operations to the cell. We have this tool changing table where the robot can drop the forming end effector, pick up a trimming end effector, can potentially pick up a welder and do welding and joining. So the goal is that in long term, we keep adding more operations to the cell and really becomes a robotic craftsman. Like a craftsman who can pick up a different tool and do different operations, the robot can pick up whatever they need to pick up for the next set of operations to do that.
That is
Wow.
dope. Would
Yeah.
you do like powder coating too, or like?
Yeah, I think we are I think the opportunities is endless, right?
Yeah,
you know,
that's
like if a tool that the robot can pick up, and it's a software with empirical modeling, all kinds of, like, we can also replicate the mind of the craftsman to some extent.
Sure.
So you can do a lot of other processes. I think we are prioritizing based on basically what the customer needs, right? So we start from sheet metal. Obviously, forming is number one thing. Number two is trimming. Maybe we go to hemming, bending, surface finishing next, and then start going from maybe welding and joining comes next. But then, you know, and then maybe powder coating, painting, some kind of surface processing. But yeah, start from forming and kind of expand from from there based on what customer needs.
That's dope. That's the dream, the fully automated factory.
Right.
Like even the robots passing from one robot to another, or like an assembly line, you know? You set
Yeah,
it up. It's dope.
that's the cool thing about it. I think that's the really exciting thing about the future, where like you can think of like autonomous AGVs, basically autonomous guided vehicles, coming in, dropping the part in each cell. One cell does some kind of operation, pick it up, go to another cell. It doesn't even need to be an assembly line. Now you can have a facility that is, the logistics of how a part moves is not tied to the manufacturing of it, right? So you can, like, through software, program different cells to do different things, and then these autonomously guided vehicles can move the parts in between them. But then through, like, click of a button, now you can make this factory to do a whole bunch of other operations.
It's crazy.
Right.
Future's amazing.
Right. I'm excited for it.
What is the process, like current day, what's the process from client all the way to finished product? They have it in their hands. Like how does it usually work for you guys?
So, so usually right now, our sales team gets a geometry from the customer. So this is a geometry that they want to form. Initially, there's some education around what is our today's productionized capability. There's some constraints around it. So we want to make sure we get a part that we can deliver. But once we have the first part, we put him through our initial software stack, which we call geometry prep, which basically gets rid of the holes, adds a skirt to the part, makes it something that can be formed out of a sheet of metal, right? With all the boundaries from a flat sheet. And then we go through our path planning process, which basically turns that geometry into a set of instructions that the robot can follow to form the part. And then throughout the forming the part and capturing the data, we also scan the part to figure out, okay, how is deformation is happening? What kind of parts we're going to get in the end? So by the end, we can automatically compare what we formed to a customer CAD. If there's any adjustments we need to make, we can now make to the part to make it even more accurate or closer to what the customer wants. Once it's done, then once the forming is done, then we go to the secondary operations. Sometimes maybe it requires a little bit of heat treat, but mostly you need to trim it. So the robot picks up a trimmer, based on the scan, maps the trimming path to the part, and start trimming the part out, adding holes. And at that point, you have a part, that's the final part that you can ship to the customer. Wow. And our goal is like basically develop the software pieces along this path so that it just gets fully streamlined. Like, you know, maybe even get to a point where the customer can go to a portal, upload their design, get guided through how to make a skirt. And then submit it, and it shows up in our manufacturing shop floor, and the technicians just put it up and make it, right?
That's incredible.
Yeah, because we also noticed, like, no one's really manning these machines. Like, we walk by and they're just like going, and it's really awesome to see that, because like, I think in a lot of aspects, like, you would almost think like, oh, maybe, you know, they have to watch it, make sure it's perfect. But it seems like these are like entirely autonomous after it starts going, and that's really cool, basically.
Yeah, no, I think hopefully you can get to a point that even prep of it is done through software. So right now, the part that is like the most labor intensive is the preparing the geometry until it goes on the robot. But a lot of work is going done, and hopefully maybe we can work with KittyCat on that, is how do we automate turning a geometry into something that can be formable and expose it through a software to our customers. So even our customer, the engineer at SpaceX, can go to this portal, use the software, prepare their geometry and submit it to us. And that way it can be kind of end-to-end fully autonomous.
That's super cool.
Even the 3D printing production facilities that have the dream of the automation of like, just give us the CAD file, we'll print it for you. I hear the same exact obstacle of like, it's in the CAD or it's some early stage where we have to go back and forth. Like, this CAD file is not right. Something's wonky about it. There's an interference here. Like, it never seems to be the dream of, yes, give it to us and we'll print it for you. It seems that it's the constant communication back and forth. And ideally we fix that one day.
Yes. No, I mean, hopefully, yeah. I think we have to fix it, right? And it's not a crazy challenge. Like, you know, a lot of it is just like, to your point, you know, you get a CAD that comes from Katia, and then you bring it to SolidWorks. Now there's holes in it.
Okay.
Now you have to go back and forth and fix those holes.
Yep.
So these are all like artificial things that we created to kind of like make this really hard.
Right.
So can we actually fix them and you know, kind of like, you know, automate this process? So I'm excited for it. Yeah.
Another
So,
question.
what was the biggest challenge you had, like making this all come to life?
It's a very good question. I think challenge is obviously what excites us. So like, you know, I think, you know, there's always challenges. I think it's a good question. I think there's always in the beginning of the process where everybody says it's not possible. Like, hey, it just can't be done. Oh, the sheet's going to be very tough to get very accurate. Like, you know, get it below 2 millimeter, 1 millimeter accuracy. Oh, it's impossible with these robots. And I think working at Relativity Space with Jordan and then being at SpaceX, kind of like you start realizing that, you know, you just got to move forward and get it done. And then it slowly starts becoming possible, right? So I think it's early on, there was a lot of, the biggest challenge was like convincing, you know, engineers, our team, external, our customers, that this is going to be done. This is possible. I think once people believe that like it's possible and show that light, they'll be like, yeah, there's a light at the end of the tunnel. This is doable. I think things become much more easier. It's always that first hurdle of getting a bunch of believers around, like this can be done, right? So I think that comes to mind. There's obviously always engineering challenges, but I think those are fun.
Yeah, those are the things that like wake me up in the morning.
Exactly. That's the reason we do this, because we love it.
Yeah.
But it's that mental barrier that's probably the hardest one to get past.
Yes.
In the beginning.
Yeah, like, you know, kind of put aside your experiences and what you thought the robots can do, what the software can do, and just plow forward and get the first version out and see what happens, right? So I think that's the biggest barrier and the biggest challenge. Once you recover from that mentally, then it gets easier.
That's super cool. I do have a weird question.
Let me put my phone
Do
away
you
one.
all have an aversion to googly eyes on robots, or?
We had some of them. I think our process devs actually love it. So I think actually this robot used to have one. They took it off probably for this.
We're gonna mail you some gigantic eyes.
I would love that.
Okay.
Gives him some character.
Yeah.
You can look him in the face.
Yeah.
I love that.
All right, let's take a look. See if I got it.
That one was on the list for us.
That was actually on the list. She's been saying that for like the last 45 minutes. She's like, they really need googly eyes.
I know. I agree. No, I agree.
So first, how much maintenance goes into the robots? Like, do these break down constantly, or are they pretty good on their own?
There are, I think, during the development, obviously, you know, you're constantly iterating on the design. So during that phase, by design, you know, things are constantly breaking, so you can show the failures, you can fix it. I think what we call the productionized capability, that is pretty reliable, right? We haven't seen a lot of like degradation in our productionized quality or maintenance there. Obviously, every system requires, you know, every few thousands of hours that you run the system, you have to, you know, make sure the bolts are all, you know, kind of torqued to the right torque, and, you know, everything still is on the part because they're moving. These are moving systems, right? But overall, yeah, and I think we haven't seen a lot of challenges with our productionist capability, but, you know, we're always pushing the envelope on what needs to be done, what kind of a material we can do, what is the next design of our forming end effector. So those are the systems where we spend a lot of our time kind of iterating and fixing the problems with.
Sure.
Yeah.
How long, so Machina started in 2019, correct? And so how long did it take to get from all the testing to finally get your first production part? Like, now we made it.
Yeah. It's actually a tough one because I think our philosophy it's a tough one to answer because our philosophy was, day one, do not spend time in design and then go and manufacture, you know, because I think that was what's failing generally with the manufacturing industry, where, you know, A lot of people would say, okay, I'm going to do 10 years of waterfall design on this system. And then after it's ready, then I'm going to productionize it. For us was like, day one, get a customer geometry,
Oh, wow.
right? Let's form that.
That's good.
Solely focus on forming that,
Wow.
right? Two things happen. One is you get a customer invested in your process. You know for sure you're building something that there is a need. I think our first customer was NASA. And we were like, okay, you don't need to form the world. We just need to form one geometry,
Sure.
right? And that focuses things a lot. I think we put out in 2019, we founded the company. Early 2020, we started putting the first cell together. By May 2020, we had our first cell. And I think we formed the first part for the customer 2 months after that.
Whoa, that's
Right?
cool.
2 months, 3 months after that. So, but again, at that point, we could form that part, but maybe not a lot of other things,
Sure,
right?
sure.
But the learnings from that, okay, how much of this can we generalize? And then as we're moving to other customer parts and making another part and another part, how do we make sure we build a stack of generalizable techniques and knowledge in the cell, right? So we kind of approach it slightly different than what traditionally industry does. We're just very iterative, always work with the customer part.
I think that's really smart, though,
It is.
especially for motivation too. Like if I'm working on this part and I'm working on the robot and I'm trying to build something brand new,
Right.
and I know we already have a customer that's ready and willing to pay,
Right.
but we have to make their part. And that's a huge motivation factor for
Right.
me to really get to see this thing be brought to life.
Yeah, no, I agree. I think a lot of times people focus on building systems that, like, by the time they're done, the customer doesn't need it anymore,
Yeah, that's a good point.
right? So
Mhm.
especially if, like, with hardware systems, it takes 10 years, 5 years,
Oh,
6
yeah.
years. So, like, at least you get rid of that problem. You're like, okay, this is something the customer needs. I think the downside of it, generally people get excited. The downside of it is engineering can become a little bit more challenging because, like, a lot of time engineers would love to be, kind of boxed off and then kind of work on developing something and put it out there. When you bring in customer requirements, their life gets a little bit turbulent, right?
Sure.
But I think overall, I agree with you that it's probably a better way to build a product as opposed to, go into a lab, build something, and come out and say, hey, it's ready,
Yes.
and then see if anybody needs it.
Right.
So, no, that's super smart.
I don't believe I have anything left.
Yeah, I think that was all we had.
All right, awesome. That was a good
But yeah,
question.
thank you for your time.
Of
Yeah,
course.
thank you
Appreciate
so
it.
much.
Thank you.
This has
Yeah,
been
no.
great.
All right, so for our viewers, can you please introduce yourselves and kind of what you do day to day here at Machina Labs?
Sure. So yeah, my name is Ashkan. I am robotics engineer manager in Machina Labs. Normally, most of my job daily is half of it is like doing a technical work and being sure that everything is running here with the other engineers we have on site, and also developing new and then adding more engineering works to be sure that we are actively developing new features. So it's in kind of like an evolving technology that every day we are trying to make it better and better. So that's half of it, and then the other half is to just be sure that the team that is right now we have 8 people, and then we're actively also trying to grow the team. We're trying to I have to be sure that the team is also on track, and then basically managerial duties that I'm doing.
I'm Naghmeh. I'm also a software engineer. I work directly with Ashkan, and the same thing, trying to develop new features every day. And then meanwhile, we are helping other teams to just keep the cells running. And if there is a bug or anything, we all work on it to solve it as quick as possible.
That's cool. That actually leads to one of my questions. So, how do you ensure that the software on the robots is the right version? And then also, do you devote a robot to development and dev versions or stuff like that?
Yeah,
a
great
good
question,
question.
actually. So I think in Machina we have this really interesting experience that I don't know many of the other startups they have. It's like we have real customers and then we have a production line. So while we are actively trying to develop, we also have to have a software stack that is fairly stable for our production line. So we practice most of the agile development that other software companies they use, but we have to be more careful. So not only we do for our software testing to keep everything stable, we do unit tests, but we also do functionality tests, integration tests. And we also, even on top of that, because we have to be sure like the bars are really high, we also have R&D cells. So our team mostly dedicate one of the cells and shield it from the production team, and then we use that one to do more testing. And then as soon after we realize that update is stable from the develop branch, then we push it to the production. So production cells, which most of the cells are, they're always different from the chain of the updates and integration that we are using.
That's cool. And you can like just push it over the network, or is that okay?
Yes and no. So we have a server and then we have robots. So it's actually, there are multiple processes here. So we have a server computer, and then we have an industrial PC that communicates with the server. And then the industrial PC also communicates with all of the other modules in the network, which are 2 robots. Each robot comes with its own computer, and then more PLC and sensors in the network. So the code that sits on the robot, and then those are kind of not connected to a network, so we have to manually push those updates, but we do version control for all of them. The software on the IPC and the server, those are traditional computers, they're traditional type of softwares. So yeah, we just use like normal updates and pushing.
That's cool.
And we just recently changed the software. So, sorry. We recently changed the software, and then this R&D team all work on the new features for the new software. And yeah, that's the only thing that I wanted to add.
That's
cool. I noticed, because I looked behind me for a second, is the first step in the robot, is it to make the topology, if you will, of what it's going to form?
So we basically have different forming strategies, correct? You can form from outside to inside or from inside to outside, depends on what features, each one has a pros and cons. And it mostly pros and cons comes back to the residual stress in the parts later when you cut it. So if you look carefully, the sheet is kind of bounded on 4 sides. So during the forming, we pack lots of stress inside the part. So one of the ways that you can limit the residual stress is to adding some rebars and bounding. That's the feature that you see normally at the beginning of the part, that we kind of like trying to bound it. What we also do sometimes is during the forming, we kind of come back and then do a bunch of shadows of future runs, future layers on unformed part. We should look at it as like a rebars. We are trying to reinforce the unformed area. So if you grab a flat sheet and then you just like try to move it, it's really flexible. But if you add a bunch of features on it, it kind of reinforces that.
It makes it stiff, yeah.
And the best feature that is not going to interfere with the part is future layers that you're going to do anyways. So we use that trick to reinforce it.
Yeah, you can see it now on this sheet that there are some lines that are like the project of the future layers.
Wow.
It's really cool.
Yeah.
And if you don't have that, it probably becomes wobbly after like a couple of hours of run.
That makes so much sense.
I want you to ask the...
Oh yeah. Have you all accidentally hit the ceiling, because it looks like it's like perfectly sized, basically?
Oh yeah. So you want to go first?
Yeah, so that happens usually when we manually try to move the robot. One accident that happened was just hitting one of the lamps on this side, but the lamp is flexible, so nothing happened. But yeah, when it's on auto mode, because it tries to just follow a path, usually nothing happens. It goes just to the same location that we asked to, but when manually we try to move the robot from one side to the other side, we look at the tip and then suddenly something else might hit around.
How often are you transporting the robots from one spot to another, or do you usually keep it in one spot?
We don't transport the robot usually from one side to the other side, mainly on the same rail when we try to move it around. That happens, but not physically moving the robot.
Sure.
So the robot has 2 modes basically. One is the auto mode, that it listens to either a pre-programmed commands in the robot or the stream of command that comes from the server. That's one mode. The other mode is you can manually, what we call it, jogging. You can manually, like there's a joystick, and then you can move the robot and move it. That is actually when most of the mistakes happen. Because
When there's a human behind it?
yes, exactly. Robots normally listen to like what we ask. They don't make like decisions. So yeah.
I'm curious, like how, because these are like KUKA robots. Like, do they give you like an SDK, or like how do you program against it? And is it like a cool interface, or?
So actually, that's a great question. These robots, industrial robots in general, they are really well optimized to do a repetitive tasks. So if you look at lots of the factories, like you can see these robots doing lots of tasks really quickly, and they're really reliable. So that is the main purpose of these. What we are doing is a little bit unorthodox in some ways, and they do have some interface for that as well. But saying that, you need to reinvent the deal that like they made for their own side, like in a big portion, and that makes it a little bit challenging. So SDK wise, yes, you can broadcast a stream of commands to them. Each brand has its own standard. It's fairly simple to actually get that up and running, but then you basically have to have a motion planner like that. Be sure that the command that you're sending is stable, and also everything is real time. So for example, KUKA wants a new command every 4 milliseconds.
Oh, wow.
So whatever you do, you have to have that command ready to go in 4 milliseconds. If you miss a deadline, for safety, they fully stop, and these robots can move really fast. So the sudden stop is actually, you can feel the whole shake upstairs.
That's crazy. So that's like really, you have to have really low latency.
Yeah.
Which
Actually,
that's a hard engineering problem in and of itself. That's nuts.
Yeah, that's one of the main challenges, especially because it's not only one robot, there are two robots in front of each other, and these two robots have to be synchronized.
Yeah.
So if like one of them delays and the other one keeps going, then it immediately applies too much force, and it can tear the sheet, or it can make a big accident at the same time.
That's a really cool engineering problem. Sorry, now I feel nerd-typed.
Can you explain what's currently behind us right now?
Yeah, sure. So one of the needs for our whole production is that we be able to deploy, have a portable cell that we can send it to somewhere, form a part, and then move it to somewhere else, because we don't want to make all the parts here and then send it. It could be in a different country, different location. So this is the new cell that we have. We can put it, it's designed to be on the back of a truck so that we can move it to somewhere else. And yeah, we don't have the robots on top. It's just the frame, the base, and then yeah, we will put the robots, new software, and then it's ready to go.
One thing I also want to clarify for those that are watching is a cell is two robots and the frame.
Yes,
correct?
that's correct.
Okay.
That's correct.
How heavy are these robots typically?
Actually, so we have different types. So we have KUKA 1000 series, they call them Titans. And then we also have KUKA 500. So each one is capable, one of them is 1000 Newton, the other one is 500. And then we have FANUC. So they have a different variety, plus the rail that comes with them. So each rail based on the type of the robot is different. I don't have the exact number, what's the add up, the weight for each cell, which is two robots, two rails together, plus the frame. But in general, it's a really big number.
I'd imagine, do you have to reinforce the ground then?
Yes. Yeah, that's one of the challenges, because these robots apply too much force, so the base had to be reinforced. So all of these concrete change to be reinforced enough for the force that they apply. Yeah, you can.
Yeah, and then you can see that challenge transfer also to the portable one.
Yeah.
So for the portable one, that's why we have to come up with this really reinforced platform as well. Yeah. Because when these robots are forming, they're kind of really close sometimes to their maximum force and torque that they can apply. So you can imagine that it's just Newton law. So the whole thing also goes to the support, which is either the ground or the platform. So if there is any deflection either in the ground or the platform, the robot will lift itself up or either make a crack in the concrete or just bends the platform.
Yeah, that's nuts. And I also assume that like wherever it's going must have like the power capacity to actually even turn it on. How much power does it draw?
Shockingly not that bad actually.
Oh,
I
wow.
thought like this thing gonna like take so much power. I think we did the math. At some point we can say that like if we add a little bit more solar power, like we might be able to even claim that we are green, because these are really efficient.
That's crazy.
Yeah,
that
it's
I was
insane.
like,
That's
whoa,
not what I
okay.
was
Yeah.
thinking.
Okay, that's nuts.
You mentioned, so this is your deployable setup. Do you have to assemble it on site, or does it go disassembled and then you have to assemble it?
Some parts of it, we can assemble it here. Some parts of it, when it arrives at the location, then we have to assemble. We have to do it. Like some, for example, the cabinets, basically the computers for each of the robots can be deployed here. Everything could be done. And then some things like the calibration of the robots, they have to be redone after we set it up, like in any specific location.
Yeah, they like
The wirings, everything could be done
yeah. So
here.
the goal is to have the least amounts of disassembly every time you want to move the platform. So the robots, like this specific one, we are deploying it without a rail, but we are also making another one that will have a rail.
Wow.
And then again, the goal is to have everything assembled as much as you can, so that the redeployable process redeploying process takes as least as time as well.
Oh, cool. And if a customer like had one of these for 6 months, would they get like the software updates you all push internally to them as well?
Yes.
Oh, that's cool.
Yeah, that's the plan.
That is our plan. Again, it depends on the customer. So, in general, metal sheet forming has one big challenge in it, which is as soon as you form a metal, it takes so much space to move it and to store it. So that is actually one of the. I remember it's a side story, but my dad actually was working in setting up a factory for metal cans for sodas, and it's insane that like some factories, some companies, and some countries, they import those pre-filled. So like there is like a huge shipping container that almost like 4 of us can lift the material inside it, but it's just a metal sheet that is formed, and now it takes so much space.
Wow.
So what they want is like these platforms to be able to deploy it everywhere, but then based on some of their applications, some of them actually don't want to be connected to internet.
Yeah,
Depends
yeah.
on the
Like air
buyer.
gapped from the world, yeah.
Exactly.
True.
So for some cases that actually one of our platforms is the case, that that introduces lots of new challenges to us.
Yeah.
It's not connected to the internet, so we cannot update updates automatically to it, and that becomes a new headache. That how should we do that? How should we apply? How should we provide maintenance for that cell?
Totally.
But as you mentioned, for those that we can deploy and we can connect to internet, then updating those requires some updates on our backend to be sure that this infrastructure is properly linked with ours.
Cool, yeah. That's it.
What is the benefit of having the rail versus not having the rail? Is it just a larger sheet that you can
Yeah,
kind of form over?
it's just basically to increase the workspace
Okay.
in one axis.
Very cool.
Yeah, and then you need to look at the workspace, as you mentioned, by like a usable workspace. So just reaching is one thing.
Yeah.
Being able to apply the needed force and torque in that point is another thing.
True.
So you can imagine if the robot is extended all the way out, it has less capability of applying force and torque.
Sure.
So to compensate for that, you move the base closer with the rail.
Okay.
We always try to make sure it's in the most efficient orientation and position in order to apply the highest force.
That's cool. Yeah.
These are the FANUC robots. So again, different manufacturer, has a different hardware, different internal computer, and has different interface.
Okay.
So now you have to imagine that, like, okay, that's a new challenge for us, that also, as soon as we moved to this one, we were also accounting that, okay, maybe tomorrow we need to also move to a third type of robot.
Yeah.
How should we make our software stack to be sure that with the least amount of modification, we can make it a plug and play and then like make it compatible with different type of like future expansions of robots brands.
Oh, interesting. So I don't know. I guess in my head, as a like software person, I would use like some sort of interface or something like that. Is that what?
So yeah, like your previous question, each of these are like these black boxes, and their output might be different, and the interface that we make to talk to each of these black boxes have to be different.
Yeah,
but
that's
we are
hard.
trying to make it like in a way that it won't be that different, so it would be easy to deploy on like a third kind of type of like robot or any different hardware.
That's cool. So what would be then the like kind of gains that you would get from like say this robot over that one or vice versa?
This specific one, we haven't started forming with this type of robot yet, so we don't know how much are we gaining or losing. We are doing in the like earlier stage like tests with it, but this was mostly because one of the specific customers for the portable cell requested the robot with this type of with the cell with this type of robot.
Wow.
Interesting. Yeah, I like that color. So yellow is my favorite color. Not that that matters.
So actually, you can order them with whatever color you want.
Oh, really?
Yeah. wow.
So some companies, especially like KUKA, like the color we have is the stock color, but you can order them. I think Relativity
Black?
ordered them black.
Yeah.
Ah.
And then I think that caused some issues. I don't know if we can say that, like
Wait, really? The color? That's nuts.
because it absorbs heat,
Right.
So
Oh.
and they do welding.
Right.
So
Damn.
Yeah.
Okay, that's crazy.
I don't know that.
I don't know it a whole lot either. But
That's so crazy. You gotta get some different colors then if you get to choose.
I know it's also so common to order them in white, but
Oh, okay.
also if you go to Universal Studio and like the Harry Potter ride is one of the coolest one. If you look inside, you can see it's actually those robots, and they just
What?
paint them in black, and then the seats are just sitting in at the end effector.
I did not know that.
It's just
That's
a huge
so
track
clever.
that has
Yeah.
one of those on it, and then which is it makes sense. Like the cost-wise, everything. These are great options. Instead of making everything from scratch, you just buy them and then modify them for your.
That's
Wow.
cool.
Yeah.
Yeah, they're really reliable.
Was,
Yeah, that's
was
nice.
there anything in your past, like both of you in your past, that was similar to working with robots like this? Or was this a huge challenge you weren't ready for?
So the thing is, like, I've been using lots of small robots, small like arms, but the concept is the same. But the main difference, in my opinion, was having the industrial PC involved. That's the part that makes it different, because like the kinematics, how they work, the programming side, all of that are the same, but the main challenge is when you want to make everything real time and then you bring this industrial PC in, then it involves lots of other issues, but not at this scale.
Sure.
For sure.
Yeah, and in my background, so actually I have a really like not interesting, like a weird background. So my undergrad was in mining, and then
interesting.
I came to US, did a master's in civil, and then at that time I did like some image processing, mostly in civil, and then I was working in a mine, and then I left there, started this robotic journey. And the whole time I was in most of my research was to making robots. So that's actually like a deep, kind of quite opposite. Like Naghmeh was mostly involved with like using robots, and I was making robots. And then when we both came here, it became like a proper tool skill set that we both brought together.
That's
And yeah, like it's
amazing.
totally different from what, like from my research and my previous projects that I was doing, because I was building everything. I was the king in the whole territory. I could do everything I want. Here I have limited access. More access comes with lots of like more like overhead work that you have to do, which is tough. But like at the same time, you can do like much more things with off-the-shelf robots, they're more reliable definitely than something that I was making, but at the same time I have less access. So
That's
it's
right.
a really like I had to recalibrate
It's a
a lot.
trade-off.
Okay. Let's go see some more.
Cool.
Yeah,
Sure.
please show us around. Talk all you want.
Also, there's like definitely not space for like a whole nother cell.
Yeah.
Oh,
It's
yeah.
like packed.
Yeah, which is actually a good thing to bring up is you guys are growing so quickly and you are running out of space.
Yes.
Are you looking for more space currently?
We are. One issue is, as we talked before, we need a specific height, and then warehouses. We also want to be fairly close to here because this is a good location for us for customers. Again, after you form it, shipping like form parts is a challenge.
Sure.
So it's then with the specific height for the warehouse, it's a little bit challenging to find the correct one. But for the next phase, we have to expand. Like this warehouse is maxed out at this point.
Got it.
Yeah, wow.
Yeah.
And this is old reliable as I know it, right?
Yes.
This is number one?
Yes.
Okay.
So this is kind of how the whole thing started. So
Wow.
I think at some point this was the whole Machina Labs.
Wow.
So like inside these fences, so we bought the used robots and we started forming with them. I think there was a photo engraved on wood behind you on the fence, at the end of the fence, the yellow fence.
Oh.
You can
Oh
see.
yeah,
yes.
look at that.
That's cool.
So that was one of the other parts that we made, and Bobak and Ed, it was like mostly like them with like I think 2 more engineers back in that time. But here was a shared makerspace like area, and then this was the limit of the existence of Machina Labs. And overnight, as far as I know, overnight they had to push their desks back in the cell because that was what they had.
Oh, they didn't have the other
Yeah.
space. Wow.
Again, things that I've heard.
Sure.
But yeah, so this is how we started. We bought the two used robots, and then they are older version. Like the horse store capacity is, I think they're like 500. But then they also come with a much older cabinet. It has again its own pros and cons. It's less responsive, but also like meaning that from your side, it's kind of more reliable.
Oh, cool.
Correct,
Okay.
because you have more room to make mistakes.
Nice.
So that's how it started, and then after we were forming with it for a while, then we bought cell 2, which is that one,
Ooh, yeah.
which is that cell, and we can walk that way and we can go over
Sure.
the
Oh, cool.
details. There are some stories there.
Go for it.
Yeah, this is actually our R&D cell.
Oh, cool.
Yeah.
Cool.
We are running
That answers
lots
the
of air
question.
path with
So
it.
this is the last cell that we're going to deploy.
Okay.
And this is our R&D cell. So we basically have deployed this and jumped through the line of deployment because now like production cell has no interest in it. So we can do all of the tests that we want on
That's
it without
very cool.
disturbing
awesome.
the production cell.
So this is the fun one that breaks.
Yeah.
Yes, all the time. Yeah. So after cell 1, we got this cell. So this is cell 2, and we actually had to change one of the robots. The main robot that came with this cell is the one behind you here. But basically, it's an like we upgraded one of the robots, but we bought these 2 again used market. We didn't have that many options, so one of them didn't come with a rail. The other one came with a rail. So we called them Thomas on the rail and Princess, the one that sits on there.
That's cool.
Unfortunately, we had to replace Princess.
I was gonna say
I was
she,
like, that looks
she
really
looks
good.
pretty.
Yes.
Yeah, so
She is
Princess
pretty.
Yeah. So we had to change it, and you can also see how we evolved. I forgot to mention it on cell 1, but even like back in that time, the main concept was to get these cells up and running to show the proof of concept for the technology. But then slowly and gradually we realized that, okay, we want to be a fully automated factory, not just a proof of concept. Then over there, everything is manually clamped on the frame. So we had lots of manual clamps that we were using to do it. And then here we slowly started to use hydraulics.
Ooh,
and then
cool.
if you go to, but again, Arduino, everything was ad hoc. We were at earlier stages.
Sure.
And then if you go to brand new cells, everything is fully automated now. We have PLC that controls the frame. We have sensors that monitors the pressure. Also, everything is controlled by the server. So the ultimate concept is at some point we want to have a queue of tasks for cell that is being controlled by a central control system. And based on the queue, we also have auto sheet loading. So each task will assign to each cell, and then the cell goes through the queue of tasks, and then it automatically goes and picks up a sheet loading tool, grabs the sheet, puts it on the frame. Server asks the robot and IPC to close the frame, and now the sheet is secure. So it then picks up the part, forming tool, and then forming the part, and then drop it, scanning it, cutting it, offloading it, and then going to the next one.
Yeah,
Wow.
that's another feature that you mentioned, which is changing the tool automatically. Right now, it just knows if we have like a station for different tools, and based on what the robot wants to do next, it goes and grabs the tool that it needs, it fastens it, and then it tries to just run the form with it, or sometimes cutting the form. Or
That's really cool.
We can
Different
actually
features.
show you guys a demo of like how the robot changes the tool.
Yeah,
warheads,
okay.
and-
Please.
Yeah.
I have a question about this one still
Sure.
though, because like this one is really unique because that robot, like they are perfectly synchronized when they go, but that robot's going to be going on the track and this one's not, and so like it's hitting a different software path, but it's still going to be synchronized, and that's kind of nuts. To
Oh
me.
yeah. So that is a great question, and that's one of the reasons that we're using these off-the-shelf robots for now. So what you do is we don't take over the forward and inverse kinematics. All we ask the robot to do is we ask it to go to this specific pose in the global coordinate frame.
Oh, okay.
KUKA, which is the robots, take care of how the rail should move, which joint has to go to where to get to that point. So
Oh.
for us, we don't really need to do much. We just ask them, hey, I want you to R1 to go to this specific, robot 1 go to this specific position, and robot 2 to go to this position, which is across the sheet. They take care of that. So if there is a rail, they utilize it. If there's not a rail, they don't use it.
That's really nice. That's cool. Okay,
Yeah.
that's dope.
For the one that's standing still or does not have a rail, do you have to nail or like bolt it in a very precise location?
No, that's the thing. So as long as it's secure,
Okay.
you're good. Because after you secured everything, with the same thing with the rails,
Okay.
you can put everything with the best that you can do. Because again, these are heavy machines, so you can't really do much like correction at some point.
Yeah.
You have a limited resolution for correction when it's heavy. But after everything, we have a really precise calibration process.
Got it.
So
Okay.
when we calibrate them, we register both robots at the same global coordinate frame.
Okay.
And then we use that global coordinate frame for everything.
That's cool.
basically, once we calibrate the tip of each robot in respect to like the base of the same robot, and then after doing that, we calibrate tip to tip of the robots in respect to the frame. So we know the location of everything, so it doesn't really matter where was the beginning
Got
of
it.
the
That's
robot.
cool.
Is that calibration process, does it take quite a while?
We are in the process of automating that as well.
Okay. Yeah, awesome.
Yeah, and
Yeah.
and for example, that's a great example of needs for things that we did not know it's a problem. For example, you calibrate these robots maybe once every few months, but then when you only have 2 robots, it's fine.
Yeah.
While we're growing, we realize that like this is now becoming
Yeah.
a thing. Like we almost have to have one person on the clock just to do this.
Got it.
So now we're trying to automate it. We're trying to find a way to automatically calibrate these 2
Yeah.
robots together. And again, we need to think of this is specific need of having 2 robots calibrated properly with respect to each other is something that is not that common in the industry. Like the
Yeah.
collaboration between these 2 gigantic robots with high velocity, that close to each other, with almost no room for forgiveness in error. That's a unique problem for us. So we can't really use the off-the-shelf solutions anymore.
Yeah, that's cool. That's a really interesting engineering challenge.
And want to jump to the demo?
Sure.
Oh yeah.
Yeah, let's do it.
That basically you have two robots that they think they are in a position, but they are not. They're in separate, different positions from what they think because everything is bent. So
to the deflection, right?
yeah, exactly.
Yeah, they deform.
And so you form a part that is not perfectly matched with the part that you were trying to form. That's one issue. And then the other thing is sheet also deflects. If you look at that part, it's been running, it's been clamped from 4 sides, but from the clamps to the beginning of the part, still it's a sheet that can deflect. So while you're forming, the whole thing is moving back and forth.
Yeah.
So at the end, you form a part in a position that is not matched. Even if the robot is perfect, even if the robot is not deflecting, the location of the part is different from where you think you're forming.
Yeah.
So now let's think of you are a customer. So we call the process that is skirting. So in 3D printing, we have support material, which is a part of the material that is inedible. You have to form it to form the real part. We kind of have the same issue. We have to make a part. Sometimes we need to form some areas that they're not part of the real part, but we have to form them because there's no other solution around it.
Right.
Like if you look at this part, this is the real part. The rest is like a support material. There's no other way that we could form it.
Right, it's not physically possible.
Exactly.
Got it.
So, or like that one is a better example.
Oh, interesting. Okay.
So like here you can see like this could be the part only. All of these are extra materials, but we can't send this to the customer.
Yeah.
We have to cut it. So now going back to the problem of deflecting, we don't know where exactly is the parts ahead of time. So what we do is we form it, we come back, we 3D scan it to see where it's exactly sitting. After that, we pick up a trimmer and then we come back, we fit the point cloud and the drawing together to find out where is the best location to define it. And then we define a cutting path.
Wow.
And then
That's
we'll come back and start cutting corners.
That is crazy complex, but it makes a lot of sense. I mean, it's just nuts.
So that way it accounts for the sheet deflection while we are forming so that it's exactly, we can compensate for that. Also, sometimes it's like we can't get it in one shot. Sometimes because of the robot deflection, we need to modify some settings on our side to know that if we are making a progress, and also to know the metric for the customer. Any metal shop, any like metal sheet forming shop that you go, as a customer, you get to ask what's the metric, meaning that I gave you this part, how far is the product compared to my drawing? For that also, we need to scan in.
Got it. At some point, would the deflection be bad enough that you can no longer use the robot, or is it just a recalibration process that you have to go through?
It's a dynamic calibration, meaning that it's like a spring model.
Yeah, it just goes back during the forming.
Oh, okay.
Yeah, it's not only just recalibrating, it's just when the next time it applies the same force, it might deform again.
So when the robot is not under load, it is at the correct point. Load and so much force and load pushes the robot, it bends it. But it's an elastic bending, not a plastic one.
Okay.
So it comes back after the load goes away.
Nuts.
Oh, interesting. I'm gonna check to see if I have any other questions.
Okay.
That's wrote down a lot.
Is there anything specific you wanted to add?
I think you can show the clamping, but I don't know if you can open it right now.
We
because
can
they
open
should
Actually,
be
got
added.
every question you wrote down.
Nice.
Yeah.
We're good?
At least I have all my questions written down.
Yeah.
I'll think for a second just to see if I have
How
another
long does
question.
it take to like cool a part, like after the robot finishes, when you can actually like touch it?
Oh, they're not hot.
Yeah, they're
Oh,
not
what?
hot.
What?
Yeah.
I've been wanting to touch it. I mean, I'm not gonna go over there and touch it, but it looks like almost a little bit like melty or whatever. I don't know. It's like shinier, which made me nervous that there's wet.
There is
That's
moly.
yeah.
We add moly on top of the. So
For
some
the
of
friction.
them. Yeah.
Oh, cool.
Sorry. Go ahead.
No, yeah, go ahead.
Some of them we add WD-40 To them,
Nice.
some of them we add moly. It's mostly because of the friction that you have.
Got it.
But if you look at the tip, we can get a little bit close and look at them. They are not, well, on the inner one is easier to see.
Nice.
But you can see most of the time they're rolling.
Huh.
Oh,
Yeah, the
Yes.
tip is not fixed basically. It's just a magnet that holds it.
Depends on the pose. So sometimes they don't roll because there's no side roll friction. But most of the time, again, they're just rolling. So you don't build up that much friction.
that's nuts. Okay. Whoa. Okay. My brain just exploded because I was like thinking they were hot.
I
Okay.
believe you said this is that, right? That's the end product
Yes.
Correct.
behind us. How long would that take?
That is probably, I think, 12 hours run.
Okay.
One thing to add is we're moving really slow here. We can go much faster. If we go fast, then yes, you can see WD-40 smoking.
Barely.
Nuts.
But-
Okay.
Yes, but right now, no. Right now, we don't have like.
And
very
is it?
slow.
It's still pretty accurate, I'd imagine, even if you're going really fast.
You will increase the error
Sure.
because robot has its own trajectory management.
Yeah.
So as you're going faster, it's just a PID controller, correct? So as soon as you go faster, it's just a larger step input every cycle. So you're always falling behind even more if you go faster. But again, those are things that if we want to really go fast, we can go fast, and then on the second iterate, we can fix it.
That's cool.
Yeah, I'll think for a minute or two, and if not, we'll say our goodbyes.
Well, we gotta do speed round.
We do have
Yeah.
to do a speed round, right?
Yeah.
You two probably don't know what that is, but let's hear a little surprise that we have for you.
Yeah, I was like, are we involved with this?
It's crazy. It's not hot. Sorry, my entire mental
Well,
model
'cause
just had to shift.
Because at first we thought it was adding material, almost like a 3D printer, like a metal 3D printer. So that's when we were like, oh, the tip must be super hot to melt aluminum. But then once we realized that it's just deformation, then
Yeah.
Yeah, the concept is like if there's a metal sheet and then if there are two robots pushing against each other in front of each other, not much really happens. But if one of them is slightly lower and right in between them, you can make a really distinct pinch.
interesting.
That's cool.
That's the key, basically. That's
Wow.
the whole IP that we have. That we use that and then we propagate this pinch on the way.
Yeah, one of the
That's so
robots
clever.
always applying the force that we ask, and the other one on the support robot on the other side, it tries to apply that pinching force the whole time.
Which one would be like the support and which would be the one adding force in this one?
Force, right?
Yes.
Yeah,
this
this one
the
is applying the force that
And
goes in.
Do they have different like tools that they're using?
Right now they're the same,
They're the
Same.
same.
but it's based on you. And also, this concept is really close to milling concept. So if you have a tool that, like for CNCing, that you're milling, the minimum corner, the minimum radius of the part that you can form with it is kind of limited by the radius of the tool you have. It's kind of the same with this. So we have tools that they are like a needle. They're like 1/4 inch
Okay.
Do you
radius.
switch off like who does force and support? I just feel like this one's working really hard, and that one like maybe they should switch because it's just not fair at some point.
Sometimes, like after forming, like this way that makes a like bump, then the other robot has to come in again and make another bump on the other side. So it depends on the
Okay.
part that we need. It could be both robots that are applying force.
Oh, okay. It should be fair. I
Yeah.
feel bad for this one.
Also, sometimes there are parts that we need to come back and work on it. So if you look at some of the parts on that cell, you can see that we formed it once and then we came back and then we added features
Oh, cool.
on the formed area. So that's another thing that like sometimes for those, you may have to switch the role of the robots.
Okay, that's dope. So it becomes fair.
Yeah, we try to not discriminate.
And then for ones that you have to come back, I'm guessing you can't move the sheet metal at all,
No.
right? Because the second you move it, you are out of calibration.
We scan.
Oh, yeah.
We scan
Okay.
first because you also don't know where you formed is really where the part is.
Got it.
That's cool.
Got
So
it.
you recalibrate yourself one more time.
Wow.
So I heard you had a tour with some of our engineers. How was it?
It was great. Honestly, I feel like I learned so much. So thank you so much.
Even with my mechanical background, I felt like I learned so much about fabrication, about sheet forming as well. This has been an awesome experience, and these robots are so much bigger in person. I loved it.
Awesome. I'm glad it was a helpful tour. Thanks for coming.
So one thing we do with everyone is we have 3 questions each that are rapid fire and just whatever pops in your brain first. So you want to go first?
Sure. What is a household invention you can't live without?
This robots comes to my mind right now. We can't live without them. Maybe it's because I'm seeing them.
Nice. Favorite tool brand for like pliers or whatever?
Tool brand for
Like-
like a shop tool?
Yeah,
Yep.
yeah.
Oh yeah. My favorite tool is probably a hammer. I mean, it's a
Nice.
traditional blacksmith
I was going to
tool.
say, it's how you
can-
form sheet metal.
You can form sheet metal
Yeah.
with it. You can hammer nails with it, right? So it's pretty versatile.
Nice.
What was the last book you read?
Last book I read. So right now I'm listening to Don Quixote again,
Cool.
and I am also listening to a book about Zen.
Ooh.
That's-
And then there is I'm also listening to Dharma Bums from Jack Kerouac.
Nice.
So those are 3 books. I'm very cool. Kind of switching between.
Cool. You mentioned a software engineering background. So what editor do you use?
So I started my career using Xcode,
Nice.
but then eventually just got bought into the hype of using Vim.
Oh yeah.
So went to
user.
Vim. So before my last projects were all done on Vim until now. Unfortunately, I don't code as much. Maybe like some Jupyter notebooks,
Nice.
but that's about it.
Cool.
What is something still on your bucket list that you need to mark off?
It's a good question. You know, it's tough. It's tough
Say.
because I don't have a bucket list.
Well, what's something you'd love to do?
You know, I really want to custom build a full car using our technology.
That would be awesome.
That's probably something that I'm really excited. Just full panel, all the outside panels using this technology, because I think this is what it can make it actually. I'm a huge car fan, and you know, if you want to have a custom car today, you pretty much have to pay thousands of dollars to hand form the sheets if you wanted your custom exterior. With this technology, that can be done very cheaply.
Okay, slight bonus question.
Yeah.
What's your favorite car?
I like old cars, like 1930s Fords. Some of the muscle cars from 1960s, mostly like 35 Ford, probably 35 and 34 Ford.
Super cool.
Yeah.
If you could visit any planet, what planet would it be and why?
I mean, all the hype is around Mars now, right? So we're good to go to Mars.
Nice.
I think it's the only one we can probably reasonably visit, right? The other ones are going to be a little bit tougher. We can go to the moons of Jupiter, but I think Mars is probably the good one
Cool.
for the short term.
So that was all we had. Thank you so much for having us.
Of course,
It's been
thanks for coming.
an amazing day.
Absolutely. Thank you so much. And for everyone at home, how can they get in contact with you, or for those that are interested, how can they follow you? Just anything social-wise, what would you like to say?
Yeah, so Machina Labs is on most of the social platforms. LinkedIn is where we're the most active, but we're also on Twitter. Search for Machina Labs, it will show up. If you want to send us an email, even, we're hiring a lot of intelligent folks and smart folks, so send an email to info@machinalabs.ai. Same thing with sales. If you want to get some parts formed, reach out to info@machinalabs.ai. I'll get back to you.
Perfect. Thank you so much. Appreciate it.
One, that is a piece of sheet metal. Two,
Yeah,
it has been pushed. I mean, it
right.
is the style.
It would actually be insulting if
It
they
would be
didn't
insulting
make
if
it.
they
So
didn't make it. Yeah.
okay.
Cool. Do you want to say they even made the sign, or should I say they even
You
made
say
the
it.
sign? Okay.
You have more excitement to it.
Okay, yeah, because I'm really excited about it.